Okay, hi. I'm Leonard Pattering. I'm going to talk today about systemd. Um, I did a talk about systemd pretty much exactly 2 years ago at FOSDEM. And yeah, so that's why I call the talk the first 2 years. Okay. I'll start the talk with a little bit of around 50 or something. So the focus of systemd has always been that we kind of cover the full range of Linux itself. So we care about mobile, about embedded, and about desktop and server the same way. It basically means that the basis for your phone OS could be the same as for your supercomputer. And that's actually, I mean, that's kind of impressive because a lot of the other software, like for example, Solaris SMF is probably nothing you ever want to use on mobile. But we want to really try to cover all these different bases. And that's actually really interesting in many, many ways because quite often it turns out that problems that are specific to one of these areas, like specific to the server, end up being hugely useful on the other end of the spectrum as well. For example, the embedded people, they supplied us patches for doing hardware watchdog stuff. Hardware watchdog stuff is relatively simple. It basically just says you have this device and you ping it, and if you stop doing that, the machine will automatically reboot. It's a technique to increase reliability of embedded hardware. Now, as it turns out, something like this is not only hugely useful for embedded hardware, but on the other end of the spectrum on the server, that's also what you require for high availability setup. So yeah, we added this feature there, ended up being really, really useful on the other end as well. And there's a lot of other stuff like that. What? Like for example, what are you doing? Anyway, so and this happens like, for example, resource management. Resource management basically is what you have to do if you run a lot of servers and have limited resources available, a lot of services and have limited resources available. You need to make sure that the available resources are nicely distributed according to your rules on the servers that are running. Now, resource management has been for quite some time been important for servers, right? You want to make sure that Apache and MySQL both get an equal amount of CPU and memory. And not one gets way more than the other, and then things starve and you get all kinds of problems. Or even more, like you have a couple of customer sites running on a single server, and you want to make sure that not one customer can monopolize the CPU and the others can't. So you want to make sure that the resources that you have available on the server are actually distributed in some kind of way among your services properly. Now, this resource management also ends up being useful very much on the embedded hardware. Because on embedded hardware, usually have very little resources, so it becomes even more important that what you run on the embedded hardware gets an equal amount or like the appropriate amount of resources assigned. So, and yeah, and there are lots of examples like that. Sometimes there's desktop stuff that ends up being usually useful for the server as well. Or embedded stuff that ends up being useful for the desktop stuff. So yeah, the same way as the Linux kernel manages to cover all the bases from embedded mobile desktop server, we want to cover the same thing for systemd as well, because we figured out that most of the problems actually reappear on the other end of the spectrum as well. Yeah, we nowadays have consistently boot times of less than 1 second for user space. We'll actually do a demo here on Kai's laptop, which is lying right here. We're not going to do this on this laptop because actually the initialization times for projectors, like during boot, are a little bit too slow, so you couldn't actually see that. We have these boot times of less than 1 second for user space. Of course, unfortunately, Fedora, like as the distribution that I use and that I work for, doesn't really provide that out of the box. A couple of reasons for that. One of the bigger ones is LVM and these kind of things. We want to go for supporting that out of the box on Fedora eventually too. But right now, Fedora will boot slower. But anyway, Kai, can you show that? So Kai has a laptop here which runs pretty much unmodified Fedora. The only change is basically that we don't have LVM and very few other things not enabled. So this is already rebooted actually. It's the information from the last boot. Now what you see here now is that we will actually break down with the systemd analyze command. We'll actually tell you how the performance of the last boot was. Now we can see that the firmware, like the BIOS, really the post, the initial initialization of the hardware took 7 seconds. The bootloader took 35 milliseconds only. The kernel took...
This is not RUD.
as you might see, this like 34 milliseconds, that's definitely not grub, because grub, like already initializing grub takes a second or something like that. This is gummi boot, actually. The kernel takes 1.2 seconds, and then user space currently in this boot here required slightly more than 1 second.
There's a sleep bundle there.
In total, it's 9.6 seconds. That's, of course, not good enough yet. On modern hardware, where, for example, the firmware, like the Windows 8 certified machines, like Windows, if you want to have a certified machine, you need to make sure that your hardware, to get the certificate, your hardware needs to boot in less than 2 seconds through post. So with that in place, we can boot an entire Linux machine in like 5 seconds or so.
Can you say that's a full distro and not like some...
So if you look at this distribution, you will actually see it's quite complete, right? We have all these desktop-y things like uPower, we have UDFD anyway, we have accounts daemon, policy kit, color daemon even, like the profiling stuff, Avahi, like this is like NTPD, it's all like in GDM, it's like a really complete distribution. The only thing that is basically changing from Fedora default is that we did not install an LVM, because LVM is like, it's the major source of slowness. I mean, we have some LVM developers still away, sorry. I will just say it, I mean, has been 2 years ago and still is.
No, it's fixed.
Well, let's discuss that otherwise. But anyway, so we did show you just these numbers, like how fast it is, but let's actually see how fast it is by demoing it. Now, this is a rawhide machine, so we hope it's actually working. But, so yeah, now we're in post. These are the 7 seconds, basically. And the screen turned black when the bootloader comes. And
Oh, that's Chrome already.
so yeah, it's like hard to see, but you see actually, yeah, it just got up. It's like, that was at 1 second for user space, 1 second for kernel.
That's so dark.
It's actually gray, the machine that projects that. But you see you recognize that this is GNOME, right?
What did it change? What did it change?
It's a bit, yeah.
Something changed with the projector.
I think that maybe that's because of the, can you shift it?
I don't know.
Yeah, actually in real life, this thing is green, what we see here. Like if we see that's gray, the projector is a little bit confused. But anyway, what you saw basically is you saw those 7 seconds for the post, and then you saw the 2 seconds after the post when it was black, and then was already GNOME up there.
We thought we avoid Linux. We thought we avoiding the projector, but this
So I mean, the reason why we use this weird projector is basically that yeah, well, projectors usually take time when video modes are switched, and that sometimes or usually takes more than 1 second, so it kind of destroys the demo. But this thing destroyed the demo anyway, because you can't actually recognize that it's GNOME. But anyway, yeah, you see the GNOME 3 stuff here. Anyway, let's turn back to the slides. By the way, again, if you guys have questions at any time, just interrupt me. I'm really interested in questions. So yeah, we have consistently boot times of less than 1 second. This one wasn't, but we generally have.
In that demo, are you using the new speed up of dbus?
The kernel dbus? No. This is pretty much unmodified Fedora 19, but without LVM, basically. So it doesn't use anything newer dbus, anything that wasn't in any standard distribution. I think it basically uses Fedora 19 and maybe a snapshot of current systemd, but that's it. Okay. As we develop systemd, we have obsoleted a couple of things. I mean, obsolete here is very wide term, supposedly here. So we replaced ConsoleKit, which used to be the daemon that managed logins and sessions and seeds, by something called lognd, which is a component of systemd. It provides quite some more than ConsoleKit used to do, like, for example, proper multi-seed support. So you can actually, like if you have multi-seat hardware, like these little USB boxes that provide you an additional screen, an additional keyboard, additional sound and these kind of things, you can now plug that into your systemd machine. Systemd will recognize that it's one of these devices and will just say, here's a new seat. GDM will then pick that up and bring a login screen. So, and that's fully automatic without reconfiguring anything. So yeah, we did this console kit. It's much nicer than console kit used to be because we can rely on integration of the kernel in a way that was not available before. For example, we can easily track membership of a process, of a session, by doing cgroups magic. I'm pretty sure like 2 years ago when you were at that talk, you probably heard the term cgroups. I'm not going to go into detail what that is. But suffice to say, the console kit replacement that we did with lognd is hugely more powerful than console kit used to be. We replaced System 5 in it. It's kind of obvious. And the init scripts package. The init scripts package, I mean, in this case, it kind of means like all kinds of different implementations of that. Like the Debian has its own init scripts package, and Fedora used to have its own as well. We kind of replaced that because all the early boot stuff, we nowadays have parallelized little implementation we see, which are nicely configurable in a kind of common and similar configuration files. We obsoleted PM-utils. PM-utils had the job of suspending and hibernating the machine. It used to have a huge amount of quirks, like because like user space quirks dealing for specific hardware that exposed certain bugs. But as it turns out today, that's mostly not necessary anymore. There are only very exotic hardware that still needs that because the kernel got fixed. Like the kernel drivers are nowadays able to apply these quirks in a much saner way. Anyway, we don't need any user space components. So because systemd already managed powering off the machine and powering it on, we added, and rebooting and these kind of things, we just added support for suspending and hibernation as well, because it's kind of the natural thing. It's so that systemd can manage the entire life cycle of the machine, and that definitely includes suspending and hibernation. Of course, we did it really nicely, like better than PM-utils did it, because we now have inhibitors and these kind of things, so that arbitrary user software can actually hook into the suspend process and do something right before the machine goes down, which is very useful. For example, let's say you have your text editor and you want to make sure that text editor actually saves everything to disk before going into suspend, so that if the battery runs out, you don't lose anything. And then there are many other uses for that as well. So yeah, we replaced initd. That's probably one of the more obvious things as well, at least if you know that systemd does socket activation. I know for sure that last time, 2 years ago, I did talk about socket activation in more detail. Again, I'm not going to talk about that very much because it's very technical. But suffice to say, we do basically everything that classic initd did in systemd as well. And of course, we try to make it more useful. So we will not just cover internet sockets, but all kinds of other sockets as well, and even some things that are technically not really sockets, like, for example, FIFOs or POSIX message queues and these kind of things. We replaced ACPID. ACPID is a little daemon whose only purpose it was to when somebody presses the power key, shut down the machine. That's basically what it did. It was a bigger project, did a lot of other things too, but nobody ever used that. People just used it to, like, hook up the stupid power button with power off. And we thought maybe that's some functionality that should not require any additional software, that should really just work. It's about powering off the machine, especially since the reboot button and since Control-L-Del is implemented either in hardware or by systemd anyway. So we thought, well, maybe the power button should be handled the same way. So, and everybody needs that, right? Like embedded hardware, servers, desktops, they all have power buttons that should work as they're supposed to. So yeah, we decided, well, listening to one key is not particularly hard. Everybody wants it. Maybe you should just move it down into systemd and just do it, and it will just work. Something else we kind of replaced is syslog. That's with something called the journal. I figured it has been discussed widely in the community already. Basically, we looked at syslog and figured out, well, I mean, we have been looking into syslog for quite some time, and what we always wanted is that we can actually query the syslog logs for all messages from a specific service. However, syslog only stores linear text files from top to bottom without any kind of indexable information, right? It does not actually know anything from which service things came. Basically, I mean, it's untrusted data. Every application can send data into it and pretend it was Apache, and syslog will just store it and not care. So we had a lot of issues with that, like because we want to have a secure system where the services cannot lie about who they are, and where we actually have this information which service it did, and can index it so that the query of the log database stuff is fast. So we are perfectly compatible with, I mean, for all of this that I listed here, basically, you still can install ACPID. You can still install syslog, and in fact, Fedora does that by default. You can install init. You can install still pmutils. We're totally compatible with that. We will not break these things. The only thing that we basically can't install anymore is system5 init, because only one process can be PID1. But yeah, it's just that you don't really need that anymore, because we have it simpler and usually more powerful in the basic stuff anyway. Something else we kind of replaced is the watchdog support. I already talked about that earlier. It's something that is hugely useful and embedded on servers. It's not so useful on the desktop, but it's an absolutely trivial thing to do, and actually should really be done in systemd, because only then you have this nice chain that the hardware watches what systemd does, and then systemd watches what the services do. Yeah, it's actually very simple to use and very powerful. Then CG rulesd, I'm not sure if you guys know that, it's something cgroup specific. It basically is a daemon that tried to move, during runtime, services into specific C groups to apply resource limits to them. It was, I mean, it was a very weird thing, because it actually did that asynchronously. So instead of, like, right when the service was started up, making sure that before the service was forked off, it was already clear it would end in that C group, it would just watch what was happening in the system, apply some rules, and magically move it into that, which of course, yeah, it's ugly. Then we kind of moved quite a few functionality that was traditionally done by cron into systemd. Not everything, and we are totally compatible with the classic stuff, but there are many, many reasons why it is actually useful to have something like cron, like calendar-based timing in systemd as well. Yeah, the stuff that we have in systemd is in some ways more powerful than cron is, but in other ways less powerful. For example, we don't do user cron jobs, anything similar to that. But we basically have a calendar language now that is more expressive than what cron can actually express in its tables. Like it has a second granularity and stuff like that. Yeah, and at the same time, we kind of considered like the same problem. As mentioned, this has obsoletes, but you can still install this all parallel, and then probably most distributions will. I don't expect Fedora, for example, to anytime soon not install cron by default. I mean, I personally believe cron is a really useful tool. Like, even though systemd can schedule things by time, you would have to create a service file and a timer file for it. And admittedly, using cron and just running one line can often be easier. So this is not an attempt to kind of remove this from the distributions or making this unavailable to the administrator. It's just, yeah, we have this in systemd, and there's a lot of functionality in there that you don't have with the classic tools. So you can use it, but you don't have to. Okay, so much about the status quo, and a little bit like giving a position, like an explanation where we currently are with systemd. Is there any questions to this point? There's a question. Like, can you?
Just Jesus Christ, sorry. Just a short question. Can you essentially, if you install a Fedora 19 system, can you actually deinstall all these things and just run with systemd if you would, just to see if it would work, or?
I didn't entirely. What can you uninstall?
Just all the stuff that you obsolete. Can you just deinstall everything and just like?
Actually, you mostly can. You can uninstall init and ACPID anyway. You can uninstall syslog, watchdog, cgrulesd. You can mostly install cron, but then, like many packages drop in cron jobs. We're working on that to make that at least possible, and there's currently talk on the Fedora mailing list to port over at least some stuff to cron. We'll have to see about that in detail. You can remove ATD. can't really remove init scripts because things depend on it, but most of the stuff you don't really need anymore. sys5 init, it doesn't really exist anymore, and ConsoleKit is not shipped by default anyway anymore.
What's still in init scripts?
So, I mean, the thing that InitScript still does that is useful is static networks, like all the stuff that's not network manager, basically. But yeah, you basically can remove most of it.
Yeah, I was just wondering, so systemd interprets the FS tab right now and creates like virtual units. Will the same thing happen with the cron tab?
Yeah, that's actually something, so everybody got the question. The question is like currently FSTab is parsed by systemd for compatibility purposes, and because we actually think that FSTab is a cool thing because it's very simple and things like that, if we could do the same thing for the cron tabs. So I think the cron tabs are not a very nice language. I think it's very simplistic. So my guess is that we probably will cover cron.daily and cron.weekly, and these kind of drop-in directories because they are really super nice to use, and we can nicely integrate them in the system tree as well. But I don't think we'll do the same for cron.d. I think like for the actual cron tab stuff, we kind of assume that like at least for the Fedora case, the way it currently looks like, we might convert everything that actually installs more than just cron daily and cron weekly and cron hourly scripts will probably use timer units, but we have to see about that. But of course, even if a distribution doesn't want to go systemd all the way Fedora decided to do it, they can, on their own, write a generator for that generates this stuff. That's totally doable. It's just that it's probably not something we want to do upstream. But yeah, there's another question.
This way. Just a little question. Systemd is today integrated a lot of systems like Red Hat, soon Red Hat, Fedora, Arch Linux, but you are superseding projects like syslog, ng, rsyslog. So how do you deal with communities? Are you offering them to work with you, or? So
we actually, like before we did the journal, we actually, I talk frequently to the rsyslog guy. He doesn't like me very much anymore. I don't know why, but it's we actually we suggested, we wanted that stuff, right? We wanted the indexing, and we weren't not necessarily looking into doing that on our own. rsyslog, I mean, there are actually patches from me in rsyslog, for example, for the socket activation stuff that we do in systemd. And so yes, we did work with them, but eventually we came to the conclusion that they probably never would wanted to give us what we wanted, which is basically index stuff. They had different focuses than we had on our stuff, and then we eventually decided to just do it on our own. One of the syslog ng guys, he's he's going to be at the Hackfest, as I saw on Google Events actually. So yeah, there's cooperation there. There used to be with the rsyslog guy, yeah, is that an answer? I mean, of course, if you install syslog ng or rsyslog, it's just will work, right? We quite carefully made sure to not break anything. In fact, even if the journal records everything as well, and everything is routed to the journal, this ultimately is a good thing for rsyslog and syslog ng as well, simply because we collect much more data via the journal. Because the journal can run during early boot, and the journal actually gets connected to every single service of the system so that we get std out and stdr. And we will then forward all of that from early boot and things like that, all to that, it will be forwarded to syslog and rsyslog. So syslog ng and rsyslog. So yeah, they ultimately benefit from this in a way too, even though it's not really necessary anymore to install it by default. But I mean, there's no doubt in the world that syslog ng and rsyslog have really useful use cases for the future as well, simply because the journal does not implement the syslog protocol, and we don't intend to. It's a protocol that has grown over years, and for most of its history didn't really have a specification. So it's really it's a complex protocol because you always have to deal with the different ways the hardware and software implemented it. So we don't have an interest in that. We totally see the use case for that. Like if you have a server set up and you want to connect collect all the log data from various hardware. it's a different use case basically than the journal. But again, they benefit from the journal as well, as the journal is this concentrated thing that pulls way more data than syslog traditionally got, and we pass it on. And we pass it on with all the metadata, like if they want.
So I have a simple question. How long until systemd merges the Linux kernel? Thanks. And also the name of your blog, Owlbreaker Audio, is it intentional, is it trolling, or what? Thanks.
I didn't really get the question, sorry.
I meant how long until systemd merges in the Linux kernel? You merged already a lot of stuff like udef and so on. Thanks.
We will probably move a couple of more things into systemd, to be frank. The thing is, like, it is of course a question, where do we put the limit? Of course, there's stuff where we absolutely clearly know that we'll never move that into systemd. But basically, our definition of what should be in systemd is everything that you need to build the basic building block. And we will, but it doesn't really mean that anything was monolithic and you couldn't separate things and things went modular anymore. It just means that we develop them in the same Git repository and share more code in them. It's not unlike how, for example, the BSD model is. In BSD, much of the CoreOS user space is kept in a single CVS or SVN repository and is actually developed in sync with their kernel. And we're not going that far. We never will merge the kernel into our tree or the other way around, because that doesn't make any sense, and there are other user spaces for Linux anyway. But what we want to do is we want to like look at what the other Unixes are doing and take a little bit back and kind of like, because I think it's a good model. Like on Linux, traditionally, all these little components that consist of the boot, like for example, everything like this, there was a separate project, a separate Git repository for the bloody power key handling. It's like that's not something that really scales, because every single of these components, how trivial they might be, like for example ACPID in the most extreme thing, they re-implemented all the service management. They shared a lot of boilerplate code, and was basically, yeah, all of them recompiled, rebuilt that, wrote it in their own code, and most of them didn't really do that actually that well. So with systemd, we want to unify this, much of this really more trivial code especially, because everybody needs it, because if you share code, you can actually reduce footprint because you have less code to execute, and we improve the testability of things, because if you share code, you can much more likely actually test the stuff that you run. I mean, yeah, and then like also this stuff, like if you have all these various components that you put together in different combinations, like many of the distributions really like doing that kind of stuff, that you can use any version of the kernel with any version of udef, with any version of libc, with any version of, and all these kind of things. It explodes the test matrix. And that's actually a huge issue, because if we ever want to ship these kind of things to people, we need to make sure, we need to have a rough idea that it will actually work for people. And you don't do that like, yeah, anyway. So our approach there is, well, some of the basic building blocks should just be developed in sync, updated in sync, and tested in sync, so that we actually have a good idea. It's a question basically of how to do your design process, how you do your development process, your testing process. And we believe we should copy that thing from the traditional Unixes where they did that more in a repository. I hope that's kind of an answer. There's more.
Are C groups going to make it so that on my desktop system, if I have like a simple fork bomb, it's not going to make my desktop shell unresponsive anymore? And how's that going to work?
So there's a controller that is supposed to deal with fork bombs. I didn't entirely get the question, but it was something about fork bombs on the desktop, right? There's a controller that does fork bomb protection, developed by some people at Red Hat. I don't know what the current state of that is, and it's going to get in. I don't know. Yeah, we'll probably support that, something like that one day, if that's like, I don't know. It's a very specific question. Ask me afterwards, I think. Are there any further questions? There are.
Yeah, there is one other.
Hi, it's about compatibility with previous behavior, in particular things like FSTab. Older systems, when an FSTab failed to mount, would continue to boot, and I believe that's not always the case by default, possibly. Are you going to try and continue to maintain that behavior, or what's your behavior on failure kind of philosophy?
I didn't really get the full question, but it was something about compatibility with FSTAB and things.
Well, it's more about older systems. If FSTAB tried to mount a device that was no longer present or had failed, it would continue to boot. Now we don't do that, and it's basically a philosophy of behavior on failure.
Okay, so basically, you already in classic System 500 systems, there's already the flag called no auto and no fail. And it had slightly less of a meaning that it has for Systemd, because System 5 cared less about that. But basically, when you traditionally already had to use no auto and no fail in FSTAB, you still have to do that. It's basically the same definition, except that, but what currently happens basically, if you do not mark a file system as no fail, then Systemd assumes that it is important that it doesn't fail at boot. It might be security sensitive if it's not mounted. And then we'll actually, it will wait for it to show up. If it never shows up, then the system will put you in an emergency mode, and you have to authenticate, and will give you a little bit of log output why you actually ended in the emergency mode. So that's the approach there. But by default, unless an entry in FSTAB is marked as no fail, we assume that everything you list there must be around during boot, and if it isn't, we'll enter emergency mode. It's a little bit different from traditional stuff. It's a little bit harder, but I think it's technically more correct to do it this way.
Hi, I know that Systemd use C groups for tracking processes, but is there any plan to use LXC to confine services in the near future?
So that's an interesting question. Actually, it's one of the things I have here on the, it actually was my next slide, about container support. So let me talk a little bit about the future at this point of Systemd. I have 3 slides here about the future. I don't really like to talk too much about the future, because then we'd probably have to fight the fights of tomorrow already today, and I'm not looking forward to that. But anyway, so for the near future, we want to add more nicer container support. We already have relatively nice container support, but there's a couple of things we would like to add. Containers, for those who don't know, are basically a full virtualization where the same kernel runs a couple of operating systems basically side by side. In Systemd, that is very nicely supported. We actually ship a tiny binary called Systemd nspawn that just uses the kernel interfaces for setting up containers and can boot an operating system in it. For example, it is very useful. You can use it on Fedora to boot up a Debian system, and it will just work. It feels a little bit like the change root command you used, like the binary you use, for example, to I don't know, if your machine is broken, you mount all the file system, then you use change root to move into it to fix something. Systemd nspawn does basically the same, but in contrast to just setting up a change root environment, it will set up an entire container for you. And then you get a shell, and will do much more than change root does, like mounting things and all these kind of things. It's a really useful tool. The container support in the Systemd is, of course, not limited to this nspawn tool, which is really tiny. It can also support LXC and libvirt LXC, which, by the way, are completely different projects. Even the name might suggest they're actually the same, but they're not. Or any kind of other virtualization. The Systemd actually comes with an interface to the container manager. So it's very, very simple stuff. Like, for example, the container manager can tell Systemd the UUID that should be used to identify the system, and then Systemd will use that to initialize the UUID of the system itself. It's really nice. In the long run, we want to bring Systemd more to the level of what Solaris can do with zones. Like on Solaris zones, what you can do is you cannot only get an idea about the services running on the host, but with the same command, you can actually enumerate all the services running on all your containers, on all your zones, on the system as well. And this is all very useful functionality, and individually really not that hard to implement, and we should provide the same on Linux too. So basically that system control, if you type that, it will show you everything from your host and the containers inside. The container support in Systemd is actually really nice and can do tricks that nobody else could do before. One specific thing here is auto-spawning. We can auto-spawn entire containers on demand. For example, you have one container where you put your Apache and MySQL in, and with the container support in systemd, you can use socket activation for that, so that the host initially listens on your HTTP port, and the moment the first connection comes in, it will actually spawn the entire container, the entire OS inside of it, both Apache and MySQL inside of it, hand over that socket, and then the container will pass it on to, like the systemd inside the container will pass it on to MySQL and HTTPD. So that is a hugely useful technology, actually, because it allows you to increase the density of customer systems on your server. Because it basically allows you to run a ton load of containers on one system and actually only have them use up resources when they're actually used. This is especially useful for like, I mean, there are a couple of companies of web hosters which have these kind of one-click things where you can, with one click, set up a tested machine and then test your stuff. With this thing, it basically comes free, because you don't actually have to run something for that. All you have to do is create that, like, actually make the listen, and then if actually somebody uses it, you invoke the container. This is actually really, really nice stuff. This also goes on the other side, auto shutdown, which basically means that, we have to figure out when the container is idle to shut it down again so that you make the best of your resource usage. Now, the auto shutdown stuff is actually really interesting because what I talked about earlier about this thing that we want to cover the whole range of Linux usage from embedded to desktop to server, the auto shutdown stuff, like figuring out when a container is idle and shutting it down then, is actually the very same problem that you have on laptops, where you want to suspend the laptop as soon as the machine gets idle. And so that's one of these nice things, because we already have the auto-suspend stuff, we can extend it just a little bit and make it work for containers as well. So yeah, I hope that kind of answers the question regarding containers. So it's going to be awesome, and it is already awesome.
Just a second, there is a previous question here.
Yeah, thanks. I just wanted to ask you to elaborate on something you said earlier. You said that when you have a web server and a database server, systemd can make sure they fairly share resources. Does that just come down to managing nice levels and POSIX limits, or is it more advanced than that? Or?
So nice levels and resource limits are inherently process bound, which makes them pretty much useless on anything you want to do these days. Because Apache is not one single process. Apache is usually, it spawns worker processes, quite a few of them, and then these worker processes spawn CGI processes and PHP whatever processes. So Apache actually is usually not one process, but more like 100 or so, depending how big your system is. So actually setting the classic POSIX resource limits on them is pretty useless. Now what you can do with systemd is that it will enable you to use C groups for that. C groups is a kernel feature that allows you to group processes into one C group and then apply resource limits to it. So this stuff is kernel supported basically, and systemd gives you a very nice interface to make use of this. So you can basically say, yeah, whatever happens, Apache, with all its worker processes and everything, gets only this much memory. And it will get this CPU priority in total. So even that if when MySQL has only 3 processes running, and Apache has 100 processes running, because each of one form one group, they will still, Apache gets half, and MySQL will get half, and it's going to be evened out, right? So it actually makes resource management workable for the first time in Linux before everything else. Like before that, the only thing you could do basically is run all your services as a single process, which is completely illusionary. So yeah, I hope that answers the question.
Thanks, that's pretty cool.
It is.
Any chance we'll see user space checkpoints and restore for these containers?
Checkpoint restore? Good question. Let's just say I'm not convinced that checkpoint restore is such a fantastic idea. I don't know. I'm not sure it really can work. So the question was regarding checkpoint restore. It's basically a facility that you can, if you have a process, you can save the current state of the process to disk, and then later on, possibly even on another machine, you read that image again, and the process continues running where it is. There's a huge amount of problems with that, I think, because processes use a lot of resources of the operating system, and getting those resources like file descriptors, sockets, internet connections, whatnot, getting those back into the same state as before, to me, appears not workable. I know that people disagree on that. Maybe I can be convinced. I don't think so, but I'm not convinced about the idea. So, yeah. Any further questions? There's questions.
Where was it? No, there was another guy. Ah, okay.
What is your view on taking this systemd for, the tiny embedded applications where the flash size is like 4 MB, 8 MB, or 16 MB maximum? So is it a good idea to take up this systemd for a build root or busy box based, tiny application, embedded applications? So does it really fit there, the systemd approach? Because this seems to be very interesting because we are talking about boot times in only few seconds. So, which also involves a lot of hardware initialization and stuff like where we are dealing with so many, sleeps in the startup to, have a. The problem is really in embedded where we really want to have a gracious startup and shutdown of services, and so this looks very interesting actually. So what is your view on such a tiny embedded applications?
I'm not entirely sure I understand everything of that, but the question was basically about using systemd like on the lower end of embedded, right? So of course, if you have an embedded system that just wants to run process and nothing else, there's no point to involve systemd in that. That said, I think it reaches quite low. It's like, I know that a lot of people use systemd in conjunction to BusyBox. For example, I don't know, systemd is nowadays used in wind machines, in cars. It's built into cars, like the Genevieve people, for example, all the coming cars from any companies involved in Genevieve, like BMW and things like that, will run systemd, which is kind of, oh my God, but yeah, you find it in toys, you find it in everything already. I'm not sure how far you can scale it down, but you should know that most of the stuff we include in it are compile time optional. So you can just use with configure. It's basically like the Linux kernel itself, where you can choose while you build it what exactly you want to build. You have the same stuff in systemd as well, where you can pass a lot of flags to configure. Okay. So yeah, I think my time's over though.
Yeah, unfortunately the time is running out, so if you have any other question, just ask the speaker. We will probably hang around the conference.
Yeah.
Thank you very much.
Thank you very much for the good questions.